All right, hello everybody. So we're back. Um, as you can see, we did some work off camera, putting together a dictionary of all the definitions that we have gone through in the first 5 chapters of Vakil, just so that we have them on hand as references, so that it's not just having to look back through a ton of notes. We can just look back through a really long table of notes. But it's really not that long. So yeah, now we can go back and we can take a look at this and pick up where we left off. Um, yeah. So we left off by defining affine and projective varieties. Um, yeah. I'm trying to decide if it's even worth uploading the video from earlier. I don't think it is. So let me go ahead and explain what we did earlier, because otherwise that'll be a waste of 40 minutes for whoever watches that. So we recalled that X is Noetherian if it's covered by affine opens that look like spec A, it's quasi-compact. We said that a Noetherian scheme is integral if it's non-empty and connected, and all stalks are integral domains. And so integrality is the union of local and global conditions. And the proof of this theorem, or rather the proof sketch of this theorem, is that going forward, integral implies irreducible and reduced. Um, and a Noetherian scheme is definitely reduced and definitely integral. And then the backwards direction is kind of assumed to go a similar way, just writing out definitions, making connections mentally. Um, okay, so then we define varieties, an affine K varieties, an affine scheme, which is reduced and a finite type over K. Um, and then we said that a reduced quasi-projective K scheme is a quasi-projective variety over K, quasi being an optional word here. Then we had a theorem that basically spec of a polynomial ring mod and ideal is an affine variety if and only if that ideal is radical. We gave an example of an ideal which was not radical, and therefore was not affine because it was not reduced. And so the example was that you could get a zero divisor out of x minus 0 and x minus 0 in the way it's shown. Then we said, okay, if we have a radical graded ideal, and we have this construction, that this is a projective K variety, um, and that there's no restriction on I being radical as long as we are looking for a projective variety. Um, and so a point, then we had ended kind of by saying that a point of a locally finite type K scheme, which is just, it means not quasi-compact, or not necessarily quasi-compact, um, is a closed point if and only if the residue field is a finite extension of K. And so, yeah, point P is closed. So, picking up in terms of how to prove this, recall that a closed point P is closed if P P is a closed point in the topology. We're going to call this K scheme X. If this is closed in X, going back to the big book of definitions, closed point. I feel like there was the whole thing about like, I feel like something like P closure equals X was a thing. Does that seem familiar, Garrett?
It does.
Um, where is that? And so, oh, right, yeah. So we're interested really in this idea of the local ring and P mod the maximal ideal in P. And so this is all the stuff not vanishing on P. Mod the maximal ideal of stuff not vanishing in P. And the only way that that could be an infinite extension of K, like taking the contrapositive here, is if this is infinite, then the point P is not closed.
Yeah.
So contrapositive says that K of P extend K is infinite if and only if P is open. Right.
Yeah.
Um, well, P, if it's open, it's a union of DFIs. Um, and so then the localization at this is a union of P and well, P and X, but really we're thinking spec A, such that Fi is not in P, right?
Yep.
And we're thinking this for all I. Okay. So then OX localized at this, the localization P and X such that Fi is not in P. And this looks like the set of A over G such that G is not in P where P is such that Fi is not P. And I'm going to guess that this really is going to look like A over Fi. Right?
Yeah.
Since it's G not in P, that double negative has to cancel out. And so then the maximal ideal, I feel like there's a whole thing about the residue field, right?
Yeah.
Like this is the localization. This is AP. And so then, where did I define residue field? It's in here, I remember writing it down. Here it is. This is AP mod MP. Well, what is AP mod MP? Right? Um, hmm. What am I missing here? How how is this an infinite field extension? How the heck is this
Not
infinite
sure.
field extension? Hmm. the hell is that an infinite? Hold on, I'm Googling this. I thought
Yeah.
about it with the no thank you helping of time. Um,
Hmm.
okay. Hmm. Okay, the thing we're missing is that
Yeah.
so the residue field is the fraction field of an affine open mod P. P is closing you. Um. Hmm. So the generic point thing. Okay. Hmm. All right. It's getting there.
Mm-hmm.
So it ends up being a proof by contradiction. Okay. Okay, this isn't wrong, it's just not useful. Um, because we want to just pick um, U to be some spec A in X with P. In U and A finitely generated A algebra? Or, no, with A finitely generated K algebra, sorry. And then let P within A um, correspond to P, the thing we're trying to show something about, to be the point. So, since closeness is a local trait of P, if P is not closed in U, it isn't closed in X. So we want to show hmm. Okay, so then moving from this, the closure of P is the vanishing of P.
Yeah. Hmm. So then assume for contradiction that P is maximal. Then A mod P is a field. And that field is isomorphic to the residue field that we care about. Which is a finitely generated K-algebra.
I put your cup holder on the top shelf, like not like on the closet shelf, not those stacked.
Then basically and K
which is a contradiction. So direction 1 of the contrapositive is proven. And now we want to show the other direction. Okay, P extend K is finite implies that P is closed. Did the first proof make sense?
Yes, it did.
Okay. Let's see. Okay. Um, okay. Okay.
February.
All right. So using the same setup.
But there's also. And more.
Um,
17. You just need your schooling. And you're gonna have to keep it track.
if P is the fraction field of A mod P, and then we want to show that P is maximal. This is a surprisingly tough exercise.
Yeah.
um, the title of this video is going to be like introducing varieties and a really long, seemingly unrelated exercise. um, so we know that A mod P is a K algebra. Um, and we have that the degree of is n
And an integral domain. And so then they use magic that we haven't unlocked yet.
Huh.
So they say, according to mass stack exchange, this implies that it's Artinian algebra, which implies that A mod P, no, yeah, is a field. And then that does reasonably imply in our world that P is maximal. But we haven't unlocked that magic.
Hmm.
And then this means that P is closed in spec A.
Plus,
Thanks. Okay, I mean, like, it works. Let me define what an Artinian algebra is. Um,
plus,
thanks. Um, and Artinian algebra is a ring with strong descending chain condition. Okay. And there's a theorem that says Artinian implies Noetherian. Prime ideals or Artinian algebras have curl dimension 0. Ideals have dimension 0. And then, yeah, those are the ones that we use. Although I guess we don't really use the dimension 0 one, but it's there. Like when we say that this is n, what we really mean is that this is 0. Okay. So that took a lot longer than
yeah.
I was expecting. I mean, not like our whole session or anything, but like long enough that I'm kind of like, ooh, I did not expect that to go that roughly. So yeah, any questions? Anything you feel like you're missing here?
Um, I think that'll come up later once I start processing all of it.
Okay, yeah, that's a fair answer. Okay. And so we do get a degree out of the a definition, not a degree. We don't get a degree out of this. No, we get a definition about the degree of a closed point. The degree of a closed point P of a locally finite type K scheme or variety over K is the degree of the field extension as an example of this, in the affine line, which is spec K over T, the point where P of T is irreducible has degree of P dimension. Where P is irreducible. Proposition 5.3.3a. What is that? Hold on, I'm confused. Okay. Okay. Sorry, I'm like reading, trying to figure out what's important. Um. Hmm. Yeah. Okay. I think we're good to move on to 5.4. I'm gonna say take a look at 5.39 on your own because it's proof of an earlier proposition that we didn't really use. It kind of made sense at the time. So
Yeah.
I am feeling like I need some big picture stuff to help
Yep.
put together like the nitty gritty pieces here. And I'm really hoping that this next section is going to give some of that bigger picture stuff. Because I need that. And it would be nice to finish 5.4 in the next hour, um, but that's probably not going to happen. Although there's some it's what is the definitions? Nothing, no crazy propositions from what I can see. Okay. So this is on normality and factoriality. Um, we can now define a property of schemes that says that they are not far from smooth, called normality, which will come in very handy. We will see later that locally Noetherian normal schemes satisfy Hartog's lemma for Noetherian normal schemes. Functions defined away from a set of codimension 2 extend over that set. Functions defined away from a set of codimension 2 extend over that set. Okay. Oh, this is like a gluing theorem from earlier. Okay. As a consequence, rational functions that have no poles are defined everywhere. Yeah, that makes sense. Like regular functions. We need definitions of dimensions and poles to make this precise. So recall that an integral domain A is integrally closed if the only zeros in k of A to any monic polynomial in A over X lie in A. The basic example is Z's integrally closed. Okay, we say that a scheme, nope. A scheme X is normal if all of its stocks are normal, i.e. are integral domains and integrally closed in their fraction fields, i.e. P is integral domain and K of OXP is integrally closed. So normality is stock local. As reducedness is a stock local property, normal schemes are reduced. So theorem, normal schemes are reduced. One might say that a ring A is a normal ring if spec A is normal. Well, no definition. A is a normal ring if spec is normal. Okay, so theorem, integrally closed domains behave well under localization, i.e. if A is an integrally closed domain, and S contained in A is multiplicative, not containing 0, then S inverse A is an integrally closed domain. And the proof sketch is has a root in K show that the least common multiple of all of the AI has B times XDM plus AM minus 1 with roots in the fraction field. Ooh, I need to charge my Apple Pencil. um, well, I mean, I think it kind of has to. Um, I don't know. How do you think we show this? I mean, clearly it's closed, right? So like,
Yeah. I'm a little stuck.
it's that BX to the N plus A naught B has oh, dude, easiest thing ever.
Yeah.
This doesn't change the roots at all,
Oh.
right? Like this vanishes on this polynomial.
Oh yeah, that's right.
Duh. That's literally the same thing.
Yeah.
Okay. That makes sense. Okay. And then that is just literally the same thing. Okay. Yeah. I don't know if I'm like saying it out loud right, but like literally that is the answer.
Yeah.
um
I get what you're saying.
like the underlying polynomial with the a n I or a n minus
Yeah.
I like has to have roots in the fraction field. And then moreover that if you take off the denominator, it has to have roots in the fraction field.
Right.
Okay. Well, let's take a 5 minute break so that my Apple Pencil can charge. Be back at 11:05.
Okay.
Okay. Garrett, you back? He's gonna miss it, but we're at 6-7% battery. Garrett, you there?
I'm here.
Okay. Dude, we're at 6-7% battery.
Nice.
Okay. Never let the graduate math you study make you any more mature. Anyway, right. So corollary of this is if A is an integrally closed domain, then spec A is normal. And for schemes that are quasi-compact or locally of finite type, normality can be checked at closed points. And any point is a generalization of a closed point. So it's not true that normal schemes are integral. For example, the disjoint union of two normal schemes is normal. Sorry, the disjoint union of two not. No, the disjoint union of two normal schemes is normal. Then spec K, coproduct spec K is isomorphic to spec K cross K, which is isomorphic to spec K over X, mod the ideal generated by X times X minus 1 is normal, but its ring of global sections is not an integral domain. Okay. I'm just gonna let that one sit for a second. I don't really. Okay.
Alright.
Like if it gets sent to its structure sheaf, then it might not be. Okay. All right. Um, and I guess a theorem that I think connects to this is that a Noetherian scheme is normal if and only if it is the finite disjoint union of integral Noetherian normal schemes. Bro. What are we even doing? Okay. Um. Okay. I'm gonna leave that one alone.
Yeah.
It's probably a proof by definition. I feel like I'm just gonna embarrass myself if I try to do that right now, though, and that's I've had enough humbling for the day. I feel very contrite. um, I'll work on that in the car tomorrow while I drive for 16 hours. Associated proposition. In commutative algebra, if A is an integral domain, then A is an integrally closed domain if and only if AP is ICD for all prime P contained in A, and then if and only if AM is ICD for all maximal ideals M contained in A. So since integral closedness is preserved by localization, 1 implies 2 and 2 implies 3, we need to show that 3 implies 1. This argument involves a pretty construction that we will use again. So proof, 3 implies 1. Assume that A is not ICD. We want to show that there is some maximal ideal M such that AM is also not ICD, because that's a contradiction of our assumption. Suppose equals 0, AI in A has a solution in the fraction field of A minus A. Let I be the ideal of denominators such that RS is in A. I be ideal of denominators of S. Now I is not A, since 1 is not in I. So there exists some maximal ideal M containing I. Then S is not in AM. So the equation in AM over X shows that AM is not ICD as desired. That is a very nice construction. Okay. Let's see. Okay. Does this proof make sense? Is this construction clear?
It does.
Okay. Something I'll note that may not be clear to anybody just randomly watching this. You know, usually after we end our lecture sessions, I'll go and work through the notes a second time on paper. So I have filled up like 2 whole paper notebooks of like stuff that I didn't
Yeah.
understand the first time.
So
Yeah,
like,
same.
I don't know, because I'm basing a lot of my RU and grad school applications on this lecture series or work through book series or whatever we want to call it. I want to make it really clear that like when we move on from stuff that we're confused about, I do go back and do it later.
Yeah.
It's not just for the birds. So anyway, okay. So section on factoriality. Okay, so definition, X as a scheme is factorial if and only if the stalks of X are unique factorization domains. Locus of points of an affine variety over an algebraically closed field that are factorial is an open subset. Um,
What's UFD? I'm sorry.
yeah, I don't think we've ever actually had to use UFD anywhere. We talked about it very briefly in Galois theory. Um, so definition, well, an integral domain R is a unique factorization domain. If for every non-zero non-unit R and R can be written as a finite product of irreducible elements. And then two, this factorization is unique up to order and units, i.e. you can rewrite things in terms of each other. Other equivalent definitions. Every irreducible element is prime. Every height 1 prime ideal principle. And then R is an integrally closed domain satisfying the ascending chain condition on principal ideals. So the first definition is like what you would see in an abstract algebra class, and then the second definition is something, or all of the following definitions are things that we care about here. An example of like a non-unique factorization is like z join the square root of -5. Since 6 is equal to 2 times 3, but is also equal to 1 plus square root of -5, 1 minus square root of -5. And 2 is not equal to any k times 1 plus square root of -5 is the idea, right?
Yep.
And 3 is not equal to k prime times 1 minus square root of -5. Where k and k prime are units. And in this case, that's plus or minus 1. So does that make sense?
Yeah, that does.
Okay. So the locus of points of an affine variety over an algebraically closed field that are factorial is an open subset. And then, okay, this is a theorem. Any non-zero localization of a UFD is a UFD. And this is because we are not implicitly adding units. I think is really the main idea. Like if we're adding units, then they play nicely with the other units. And if we're not, then we're not.
Yeah.
Sorry, I don't think that's a very good explanation. Um, Basically, the thrust of all of this is that if A is UFD, then spec A is factorial. The converse doesn't need to hold. But the useful thing is that elliptic curves are factorial. Yet no affine open is spec of a UFD. Hence, one can show factoriality by finding an appropriate affine cover, but there need not be such a cover of a factorial scheme. One might reasonably call a ring A such that spec A is factorial a factorial ring. We won't need this terminology. Okay, how to check that a ring is a unique factorization domain. There are very few means of checking the Noetherian integral domain is a unique factorization domain. Some useful ones are elementary means, rings with a Euclidean algorithm such as Z, K of T, and Z over I, like the Gaussian integers. Polynomial rings over a unique factorization domain by Gauss's lemma. Height 1 prime ideals are principal, normal, and class 0 normality and class 0 domains. Nagata's lemma. Okay, that's not very helpful. Basically, use this definition. um, use this definition and use the bottom three to check not something is UFD. Okay. The other big theorem here is that factoriality implies normality. And this is attributed to a theorem that UFD implies integrally closed, implies factorial schemes are normal. And really what we're saying is that if A is UFD, spec A is normal. Okay. I think it may be helpful first to hit the examples of this stuff.
Okay.
Because there's like 2 full pages of examples, and I think that that's going to be a better use of time. Than trying to prove that. So affine K space. projective space, spec Z are normal. And really, this is by showing that that they're factorial. So we want to show that stalks are UFD for each x. Well, the stalks of affine n space. Well, so has OXP is AP then that is, or no, sorry, this is KP. This is K localized to P, which is field localized at P, which is UFD. Similarly, so PNK is proj well, this has OXP equal to K over X localized at P, which is also the same thing. And then spec Z has OXP equal to Z localized to P, which are the p-adic integers, is a UFD. Okay. Not terrible.
No.
So exercise, let A be a UFD with 2 invertible and Z squared minus F irreducible in A over Z. One, if F and A has no repeated prime factors, then spec A over Z mod Z squared minus F is normal. And then the hint that B is a C. Integral domain sets Z squared minus F is prime. Suppose there exists a monic F over T in B over T, such that f of t equals 0 has a solution in alpha in k over b minus k over a. What the heck? Um, and alpha is equal to g plus hz, where g and h are in k over a. Well, alpha solves q of t equals 0, where q of t is equal to g squared minus 2gt plus g squared minus h2f and ka over t. So f of t is equal to p of t times q of t and k then by Gauss 2g g squared minus h2f are in a. Let g equals r over 2, h equals s over t. Reduce. Then g squared minus h squared f is equal to r squared t squared minus 4s squared f over 4t squared, and t is invertible. Okay, how the blank does that help? We introduced new variables. We introduced a new freaking module.
Yeah.
Dr. Vakil, how is this making life easier? What? What the hell? What the heliante, bro? I got nothing. Dude. How is that helpful? Okay. So what do we really want to show? We want to show that spec A over Z mod this thing is normal. What theorems do we have? Okay. If we can show that A over Z mod Z squared minus F is a UFD, then we can show that that's normal. And so we want to show that B is normal. And so we introduced a new module. Yeah, That makes so much sense. I love that. That's great. That makes a ton of sense, Dr. Vakil. What the heck? This might be the thing that I email him about. This might be the one where I finally send him an email like, "Hey, dude, I'm stuck."
Huh.
I don't know. So, okay. I'm going to throw it out there. I don't know how to solve this. And I'm very tired and very hungry. And there is 2 more pages in chapter 5 that are very interesting examples that like are tangible things to tie down the stuff in chapter 5 that has been abstract nonsense to something meaningful. I'm
Mhm.
going to suggest that since we are not meeting maybe until Monday, and since I'm driving for all of 16 hours tomorrow,
Yeah.
and that I'm a passenger for maybe 14 hours of that, I am going to work on these next 2 pages fairly thoroughly. Um, and I will present my stuff, whatever I come up with, on Monday. And then we can go in and start quasi-coherent sheaves in chapter 6.
Yeah.
And yeah, it would be cool if we could get up to Jordan Holder theorem soon, but I don't know.
All
The
right.
school's starting, we'll see how far we get. That work for you?
That does work for me.
Okay. I'm gonna go ahead and stop the recording now. um, before